Myself, BS Darshan. My USN is 2SD22EC014. I'm currently studying in 6th semester A division. My project is on code for generating generator and parity matrix with respect to given data length under the guidance of Dr. Sunil S. Matil sir. Introduction to the project is that error control coding plays a vital role in ensuring reliable data transmission and storage in digital systems. One of the most widely used error detecting and error correcting schemes is the Hamming code, known for simplicity and effectiveness. Hamming codes are the subset of linear block codes that can detect up to 2 bits error and correct single bit error. To construct a Hamming window, it is necessary to compute two fundamental matrices, the generator matrix and the parity check matrix. The generator matrix is used to encode the original data into a longer code word that includes redundant bits for error detection and correction. The, ma- the parity matrix is used at the receiver's end to verify integrity of the received data and identify error position if any. The design of this matrix depends on the length of the input data and the number of redundancy bits required. This report presents a C programming that dynamically generates the generator and parity check matrix for any given data length of k. The approach provides the practical demonstration of theoretical principles of Hamming code and illustrates how such matrices can be built algorithmically. The structured approach to generating these matrices allows for scalable and adaptable error correction schemes suitable for varying data lengths and system requirements. The objectives of the project is that to implement a C program that dynamically generates the generator and parity check matrix based on a user-defined data length, to understand the structural formation of Hamming codes and how redundant bits are allocated within a code word, to construct the matrices in the symmetric form where the generator matrix includes an identity portion for bits, data bits, and a parity portion for redundancy. To demonstrate the practical application of coding theory, particularly linear block codes, the algorithmically matrix generation. To validate the matrix properties, ensuring that the generator and parity check matrix follow the theoretical rules of error detection and correction. Here is the source code. We will run and check the output in the VS compiler. While we will run the code by entering the data length of 4, and we will get an operand generator matrix output and parity check matrix output. By changing the we will run another time by entering the data length of 7, we will get an generator matrix and the parity check matrix output while running. And this code's run by the code first finds how many parity bits are needed for the given data length. Then it creates a matrix that helps to detect and correct error errors. Then finally, it builds a generator matrix that is used to create a encoded data with error checking ability. Here are some applications. Firstly, error detection and correction in digital communication. Hamming code generated by these matrices help to detect and correct single bit errors in data transmitted over noisy communication channel, improving reliability. Data integrity in storage device used in a hard drives, memory modules, and SSDs to ensure stored data is not corrupted due to hardware faults or external interfaces. Reliable data transmission in networks employed in a network protocols and wireless communication systems to maintain data accuracy and reduce retransmission caused by errors. And lastly, foundational tool in coding theory education. provides a practical understanding and implementation experience of linear block codes, serving as an educational example for students and researchers. Lastly, the conclusion part is that the generation of generator and parity check matrix is a fundamental to implement Hamming codes, which provides an efficient method for error detection and correction in digital communication and storage systems. By systematically constructing these matrices based on the data length, and required redundancy, and the code ensures reliable encoding and decoding for information. The theoretical principles behind these matrices enables identification and correction of single bit errors, thereby enhancing a data integrity and transmission reliability. This approach not only reinforces practical application of coding theory but also serves as a foundation for more advanced error correcting code designs. Overall, the method demonstrates the critical role of structured redundancy in maintaining accurate and dependable digital communication. Thank you.